Hi everyone, welcome to my presentation. Today I'm happy to introduce PhyCV, a physics-inspired computer vision library. I'm the speaker today. My name is Yiming Zhou and I'm a PhD candidate from Jalali-Lab at UCLA. This is a joint work with Callum McPhee, Dr. Madhuri Suthar, and Professor Brahm Jalali. PhyCV has a new class of computer vision algorithms that are derived from physics, which features low dimensionality and high efficiency. On some tasks, PhyCV has comparable or even better results compared to leading neural networks, while being orders of magnitude faster. This is the outline of my presentation today. First, I will give an overview of the library, then talk about the background and history of how it is invented and developed. Next, we will go over the algorithms in the current release and highlights. First, as an overview, PhyCV is a Python library of physics-inspired computer vision algorithms. The code is open sourced on GitHub and can be installed from pip. It has got more than 290 stars since we released it in June 2022. Currently, it has 3 algorithms that are originated from Jalali-Lab at UCLA. They are PST for edge detection, PAGE for directional edge detection, and VEVID for low light and color enhancement. We will go through these 3 algorithms respectively later. Then the 2 highlights of PhyCV library are the modular code architecture and the support for GPU acceleration. To get started of the background, I would like to elaborate more on the term physics-inspired algorithms and also spend some time on the history of how to derive algorithms from optical physics. Unlike traditional algorithms that are a sequence of handcrafted empirical rules or deep learning algorithms that are usually data-driven and computationally heavy, physics-inspired algorithms leverage physical laws of nature as blueprints. These algorithms are low-dimensional in parameters, highly efficient, and interpretable. Also, they can in principle be implemented in real physical devices for fast and efficient computation. To be more specific, PhyCV leverages the knowledge of optical physics and adapts it to computational imaging. The algorithms emulate the propagation of light through a physical medium with natural and engineered diffractive properties, followed by coherent detection. The diffractive medium will apply a phase kernel to the frequency domain of the image and convert a real-valued image into a complex function. After coherent detection, the output phase contains useful features of the input image. Then I'll introduce the history and intuition of PhyCV. The algorithms in the current release of PhyCV are inspired by photonic time stretch, a hardware technique rooted in optical physics for ultra-fast and single-shot data acquisition. The technique involves the manipulation of time using optical physics, and that's why the logo of PhyCV is a sketch of a clock. Photonic time stretch was originally proposed in Jalali-Lab at UCLA to overcome the speed and resolution limitation of analog to digital converters in 1998. In the ensuing 2 decades, it has emerged as the most successful approach to real-time measurements and has mutated into many variants for diverse applications. For example, it leads to the discovery of optical rock waves, the invention of ultra-high-speed microscopy for cancer cell detection, etc. Last year, we published a new review article on a unified framework for photonic time stretch systems, which includes the latest applications and a detailed derivation of the mathematical principle. It has 4 steps in general, but the 2 core steps are the information modulation and information stretch. In these 2 steps, the incoming information is modulated onto the optical spectrum, and the spectrum is further manipulated using optical dispersion. The optical pulse propagation in the medium is governed by the nonlinear Schrödinger equation, which has 3 terms on the right-hand side: loss, dispersion, and nonlinearity. Photonic time stretch can be understood by first modulating the information onto the optical carrier spectrum and then propagating the modulated pulse through a dispersive fiber. By disregarding the loss and nonlinearity, the full nonlinear Schrödinger equation can be simplified to this integral equation. The information that is modulated onto the input pulse spectrum can be reshaped into a temporal signal at arbitrary timescale with a complex envelope as shown in the equation here. Then we convert the operator to discrete domain. Instead of using continuous variable t and omega, we use discrete variable n and the corresponding frequency k sub n. The 1D discrete stretch operator can be written as the input signal spectrum multiplied by some general phase kernel k and amplitude kernel L. Next, we further extend the stretch operator to 2D and switch the coordinates from temporal domain to spatial domain as shown here. Consider m and n as spatial coordinates in the digital image. Km and Kn are the corresponding spatial frequency coordinates. This 2D discrete stretch operator emulates an image propagating through a diffractive medium, just like a laser pulse propagating through a dispersive fiber. This demonstrates the connection between the algorithm and the optical physics. Finally, an essential step is to detect the phase of the output in the spatial domain. The detected phase contains useful features. To elaborate more on why do we need the phase information, let's look at the spectrum multiplied by a phase kernel only. Under small phase approximation, or we call the nominal near field, the phase operator can be approximated as shown in this line. Then we can get the real and imaginary parts of the output in the spatial domain. The real part can be approximated as the original input in the spatial domain, and the imaginary part is transformed in the spectral domain as shown in this line. Then, if we take the phase of the output, it will be the arctangent of an imaginary part divided by real part. Since the denominator can be approximated by the original input, taking the phase has a built-in equalization effect. So far, we just covered the nice property of phase operation in the numerical domain. But how do we come up with the idea of using phase detection? It is actually motivated by our own observations from experiments. In the 2014 paper from our lab, we developed single-shot absorption spectroscopy using photonic time stretch. By injecting femtosecond laser pulse into the chemical, we can observe the absorption spectrum in single shot. This is useful for real-time monitoring and of chemistry that occurs over short time scales. For example, in the study and optimization of combustion. The figure here shows the absorption power spectrum of acetylene gas measured by an optical spectrum analyzer in a time-averaged manner. You can see these narrow absorption lines. This is relatively clean to observe, but such measurements cannot be performed in real time. Then, the green lines represent the absorption power spectrum measured in single shots using photonic time stretch. This measurement can be done in real time, but it is clearly more noisy. To address the problem that the single shot power measurement is noisy, we developed a coherent version of photonic time stretch in our lab, which is originally published in this 2014 paper. Here, instead of detecting the intensity of the optical spectrum, as is the common practice in spectroscopy, it leverages interferometry to measure both phase and intensity through coherent detection. Okay, now back to the acetylene gas absorption spectrum. The red line represents the single-shot phase measurement from coherent photonic time stretch. It is plotted without any smoothing or averaging. There is clearly less noise, even it is done in single shot in real time. Another advantage of using phase detection is the dynamic range enhancement. According to the theoretical calculation, the even number absorption lines are approximately 3 times stronger than the odd number lines. The figure on the left is the absorption strength of the acetylene gas from the Hytron database, which is theoretically simulated and calculated with high precision. Because here the horizontal axis is wave number instead of wavelength as shown previously, the plot may look a little different, but you can observe a significant difference between odd and even number lines. However, if we look at the absorption power spectrum from measurement on the right, such a difference is masked in both time-averaged and single-shot measurements, because of spectral resolution and noise. But if you look at the phase measurement, it records a much larger difference between odd and even number lines, which is more consistent with theoretical results. Therefore, the phase measurement can be indicative of activity beyond the dynamic range of power measurements. Next, let's look at the algorithms in the current release of PhyCV. PST, phase stretch transform, is the first algorithm for digital image processing that is derived from photonic time stretch. In PST, we have a virtual diffractive medium that applies a nonlinear frequency-dependent phase onto the frequency domain of the image, with higher amount of phase applied to higher frequency features, since sharp transitions, such as edges and corners, contain higher frequencies. By detecting the phase of the output, PST extracts the edge information. The edges can be further enhanced by applying thresholding and morphological operation. In general, PST is a computationally efficient edge and texture detection algorithm with exceptional performance in visually impaired images. The original implementation of PST was open sourced in 2016 and has more than 800 stars and 200 forks on GitHub as of now. PST has been successfully applied to various applications, including single molecule imaging, wastewater treatment, digital retinopathy, and dolphin identification, etc. PAGE, phase stretch adaptive gradient field extractor, is an improved variant of PST, which detects directional edges. Metaphorically speaking, PAGE emulates the physics of birefringent diffractive propagation that is orientation dependent through a physical device. Instead of a single phase kernel, PAGE uses a filter bank with filters at different directions. The directional edge detection gives PAGE the ability to pick out structural details from images in a way that PST cannot. As shown on the left, the directions of edges are encoded into the color space of the image. As shown on the right, the animation demonstrates the detection of edges at different directions. More recently, we introduced a new algorithm called VEVID for low light and color enhancement. The physical principle of VEVID lies in the general PhyCV framework, but with some modifications in the real implementation, including adding the regularization term B to the input and a phase gain term G to the imaginary part of the output. The VEVID algorithm operates in the HSV color space, and C here means the color channel. It leads to low light enhancement when operating on the V value channel and color enhancement when operating on the S saturation channel. The paper was published in eLight at the end of last year, which has a comprehensive explanation and full derivation. I highly encourage you to check them out if you are interested. Here are more examples of VEVID doing low light enhancement under various conditions. This one is in extreme dark. This one is for an indoor scene with heterogeneous lighting conditions. This one shows the potential of using VEVID in autonomous driving applications for dark conditions. This one shows the potential of using VEVID in improving astronomy images. Here are more results of VEVID doing color enhancement, which literally makes the pictures more vivid in colors. Another useful application of VEVID is serving as a powerful pre-processing tool to improve neural network-based object detector in the dark. Here, we use a pre-trained YOLO V3 model. If we directly apply the neural network to dark scenes, it will miss most of the objects because usually the training dataset doesn't include many dark scenes. However, if we first apply VEVID and then use the same pre-trained YOLO model, the results are significantly improved without any retraining. Also, since VEVID is highly efficient compared to neural networks, it barely adds any computational overhead. To further accelerate the low-light color enhancement operation, we propose VEVID-lite, which is a numerical approximation of the full VEVID algorithm. More specifically, we remove the time-consuming Fourier transforms in the original VEVID algorithm and replace them with a closed form approximation in the spatial domain only. It further reduces the computational time without appreciable sacrifice in the result quality, as you can see on the left. On the right, we compare the frame rate of low-light enhancement at 4K resolution between one of the leading neural networks called 0DCE and VEVID in PhyCV. 0DCE contains about 80,000 adjustable parameters that needs to be trained on a dataset with images at different exposure levels. However, VEVID has only 4 parameters, and VEVID-lite has only 2 tunable parameters. They don't need training, and an empirical set of parameters will work relatively well on a large range of images. At the end, let's look at the highlights of PhyCV library. The first highlight of PhyCV is the modular code architecture. The modular code design follows the physics behind the algorithm and is therefore more intuitive and readable, since all algorithms in PhyCV emulate the propagation of the input image through a device with specific diffractive properties, which applies a phase kernel to the frequency domain of the original image. This process has 3 steps in general: loading the image, initializing the kernel, and applying the kernel. In the implementation, each algorithm is represented as a class, and each step is represented as a method, as shown here. This makes the algorithm easy to understand and extend. Moreover, GPU versions of PhyCV are built on PyTorch and accelerated by NVIDIA CUDA. The GPU compatibility significantly accelerates the algorithms, which is beneficial for real-time video processing and related deep learning tasks. Here, we show the comparison of running time of PhyCV algorithms on CPU and GPU for videos at 1080p, 2K, and 4K resolutions. We can observe significant acceleration for all algorithms and at all resolutions. Finally, let's have a brief walkthrough of the GitHub repo of PhyCV. Okay, so this is the GitHub repo of PhyCV, which has a detailed README file, as shown here. So let's look at the contents. It has introduction, the folder structure, the instruction for installation, and the 3 algorithms, some sample results, reference, and citation. So for folder structure, it has 3 folders. The assets folder contains sample input images and videos, sample results, and documentations. The PhyCV folder has the source code of PhyCV. The scripts folder contains examples of running PhyCV with Python scripts under different cases, for example, on a single image or on a video clip. For installation, the GPU versions depends on PyTorch, so please make sure you have the correct CUDA version set up before installation, and you can install from pip or from source. Then we have the document for all the 3 algorithms. It has each algorithm has a short description, and you can click the link at the end to go to a separate document with more detailed description of the algorithm. Then we provide some sample results of running PhyCV algorithms on the input image under the assets folder. And we also provide the parameters to reproduce these results. So this is for cell image edge detection, retina vessel detection, and some more results on different images. So here are the directional edge detection of a wind rose, of a sunflower. And here's a comparison of edge detection with and without directions. And then there are more results on low light enhancement and color enhancement. And finally, we have the reference and also a archive preprint, which is a technical description of this repo. Okay, so this leads to the end of the presentation. Thank you for your time, and please see more information in the archive preprint, GitHub repo, and the Wikipedia page. Thank you.